All right, so we're going to talk about chapter 12, which has to do with solutions. Okay, so what happens when substances are mixed? If you can imagine, take 3 glasses of water, add salt to the first one, add oil to the second one, 10 drops of oil, and then add alcohol to the third one, 10 drops of alcohol. What's going to happen? Well, as you would imagine, the salt will dissolve. We call that a homogeneous solution. If you remember, homogeneous just means that it is consistent throughout. Oil and water will not mix, so you can see that you'll have a layer of oil forming on top of the water. We would call that non-homogeneous. And then alcohol will dissolve also, and so again that would be homogeneous. Okay, so a soluble substance is one that will dissolve to a significant extent in a solvent. It will be homogeneous. So both salt and alcohol are soluble in water. An insoluble substance then is one that does not dissolve to a significant extent in a solvent. Oil is insoluble in water. We can use a few other terms. If both substances happen to be liquid, we can also use the following terms. Miscible means that 2 liquids are soluble in each other or mixable in each other. So we can say that alcohol and water are miscible. Immiscible indicates 2 liquids that will not mix with each other, and so oil and water are immiscible. You can use soluble and insoluble universally, but miscible and immiscible will be specifically for 2 liquids. So we would not say salt is miscible in water. We would say salt is soluble in water. Okay, so a solution then is a homogeneous mixture of 2 or more substances, and those substances could be ions or molecules. So in the previous example, both salt and water mixture and the alcohol and water mixture are considered solutions because they are homogeneous. The oil and water don't mix, and so they are not a solution. They are immiscible, they are insoluble, not a solution. Okay, so there are different types of solutions that we can have. Solutions can exist as gases, liquids, or solids, and we have some examples that will show up in the table 12.1 in just a minute. Some definitions: the solute is the thing that is being dissolved, and it's generally considered the component of lesser amount. If you're dissolving a gas or solid in a liquid, it would be the gas or a solid. But generally it's the one of lesser amount. And then the solvent is what you're dissolving it in, the dissolving medium, usually the greater amount. Okay, so this is a list of some different solutions. Air is actually a gaseous solution. So nitrogen would be the solvent, and the other gases, oxygen, carbon dioxide, etc., would be the solute. Soda water is a liquid solution made up of dissolving a gas in a liquid, CO2 and H2O. If you have a mixed drink, actually wine might be an example, or gin and tonic or rubbing alcohol or any of those kind of things, is a liquid solution where one liquid is dissolved in another liquid. They're completely miscible in each other, mixable. Then you can have a solid dissolved in a liquid, which is something like salt water. You can actually have solid solutions, which is a little bit harder to imagine, but and I would imagine that you have to first make them a liquid to mix them really well, but like any kind of alloy is actually a solution of one solid in another solid. Interestingly, that potassium sodium alloy, it says it's 2 solids mixed together to make a liquid, and according to your book, sodium metal melts at 98 degrees Celsius, potassium metal melts at 63 degrees, but when they're mixed, the melting point is lowered to negative 10 degrees. So it's actually a liquid at room temperatures. That's very interesting. And this is an example of the lowering of the freezing point when you've got a solution, which is called a colligative property. And that's something that we'll talk about later in this chapter. So this will sort of summarize a little bit of what I was saying on the previous. Gases can mix in all proportions to give a gaseous solution as long as they're non-reactive. Air, like I said on the previous slide, air is a solution of oxygen, nitrogen, and other gases. Liquid solutions are the most common. Those are the ones that we usually deal with in the chemistry lab. And what are some examples of that? Many types of salts are soluble in water. Other compounds such as sugar, alcohol are also soluble in water. So we have lots and lots of liquid solutions, the most common type. And then, like I was saying, solid solutions are often referred to as alloys. You would have to melt them first and then mix them and resolidify them. And just for your information, you've heard of brass. Brass is actually an alloy of copper and zinc. Bronze is an alloy of copper and tin. Pewter is an alloy made of zinc and tin mixed together. So those are technically solutions because they're homogeneous. All right, so what if we keep adding more alcohol or salt or oil? Well, so if we kept adding oil, we know that the oil and water will never mix. If we keep adding alcohol to the water, it will always mix. You can have 1 drop of alcohol in a gallon of water. You can have 1 drop of water in a gallon of alcohol, and they'll always mix. So they're completely soluble in each other. Oil and water are never soluble in each other. But with the salt, you probably can imagine that eventually you keep adding more and more spoonfuls. Eventually it will stop dissolving, and we get to kind of a limit. So there's often a limit as to how much of a solute would dissolve at a given temperature and pressure, and that is called the solubility, how much can dissolve. So the amount of substance that will dissolve in a solvent is referred to its solubility. If you don't have enough to let's see, if you put some solute into a solvent and it's not at the maximum, then we call that an unsaturated solution. It has less solute than is what's allowed, so you still could add more. So an unsaturated solution means you could still add more, and more will dissolve. A saturated solution then is one that is holding as much solute as is allowed at a stated temperature. And we'll talk more about temperature and pressure in a minute, because as you probably can imagine, if you heat it up, you can often add more. But a saturated solution is one holding as much solute as is allowed at a stated temperature. So here's just an example. It turns out that the solubility of salt is 36 grams for every 100 grams of water, 100 milliliters of water. So if you took 30 grams of sodium chloride and you add it to the water, it would all dissolve. And this would be an unsaturated solution because we could still dissolve some more salt. If we put 40 grams of salt, though, into that same 100 mils of water, what would happen is 36 grams will dissolve, and the additional 4 grams will remain undissolved. And so this would be called a saturated solution. And generally speaking, you don't know if you have a saturated solution unless you have some solid hanging out, which means that the maximum's been got the limit. You've gotten more than the limit. Actually, sometimes it's possible to obtain a supersaturated solution, and you can imagine a supersaturated solution then is one that contains more solute than is allowed at a given temperature. You might think, well, how is that possible? Well, first of all, they're not true solutions because they're unstable, and so if they sit for a while, eventually they won't stay supersaturated forever. For like if they just sit, or if you hit them on a table or something, or if you add a small crystal of the solute to a supersaturated So this is actually a picture of a supersaturated solution of sodium acetate. If you put a little seed crystal in there, the whole thing will crystallize. All the excess will come out. And I can't do it now, but if you want to go on the regular PowerPoint and watch this YouTube, it's just showing you a supersaturated solution forming into a saturated solution. So once all the excess comes out, you'll have a saturated solution. All right, so why do things dissolve in each other? Why is something dissoluble in another thing? Well, there's two major factors that control the formation of the solution. The first one is the intermolecular attractions. And so in most cases, what you want to remember is like likes like. What does that mean? That means if you have a polar solvent, it will dissolve other polar solvent, or ionic, since that's also charged. Nonpolar solvents will dissolve other nonpolar solvents. In general, polar and nonpolar do not mix because they won't be the same type of attraction or intermolecular attraction. The other thing that's important is the tendency toward disorder. Basically, if things are mixed together, that leads to diffusion, which is a type of disorder. And so if you have two compounds that have similar attractions, then they're naturally going to mix because of disorder, because of this randomness. All right, so like I said, like. Polar molecules will interact well with polar solvents, such as water. So this is showing a picture of a polar solute. It's a polar, of course, means that one end is more positive, one end is more negative, and here you can see that water also has a positive end and a negative end. So what happens is that the positive end of the solute will be attracted to the negative end of the water, and vice versa. The positive end of water will be attracted to the negative end of the solute. So the dipole-dipole interactions of water they're attracted to each other. Now, if you had water on one side and the solute on the other, randomness takes over, and because the attractions are similar, they don't care who they're attracted to as long as they're similar, and so the solute and the solvent start mixing, and the attractions, as long as there's some kind of attraction between them, then they're good. Okay, so again, because the solute-solvent interactions are very similar to solute-solute and solvent-solvent interactions, the disorder takes over, and it doesn't really matter who is attracted to what. They just all mix. So for example, vinegar, which is polar, will dissolve easily in water. Okay, so that's polar and polar. And nonpolar solvents will also interact with nonpolar solvents in the same idea. So if they're this time all nonpolar solvents and solutes are only London dispersion forces, very weak forces. But because the interactions between solvent and solute are very similar to solvent-solvent or solute-solute, they still randomness takes over. So for example, heptane and octane are both nonpolar components of gasoline, and they will mix together very well. Now, polar solutes will not dissolve in nonpolar solvents and vice versa. So polar and nonpolar don't mix very well. And the reason is there's very strong bonds between the polar solute molecules. So they're like, say it's water. All the water molecules will stay attracted to each other. There's very weak forces between the nonpolar solvent, but the water is not going to want to give up a very strong attraction to form with a weak nonpolar solvent, and there's too much energy needed to mix these together, so they'll never mix. So water and say gasoline will never mix because there's not enough energy to overcome these interactions because they're so different to each other. And this is sort of a picture of that. So let's say we have water on the bottom, which is A, and then say gasoline, which is B. Well, the strong interactions between the water molecules will hold A right there at the border, will hold it. B won't be strong enough to pull A away from the other strong attractions, and so these can't be overcome by random mixing. Okay, now Polar solvents will also interact well with ionic solutes because ionic attractions and polar attractions are very similar. So remember that an ionic solute is just one that has full positive and full negative charges. So they're just the extreme in polarity. So here, if we had NaCl, for example, the Na plus can be attracted to the negative end of water, and actually the waters will surround it. We're not showing enough here. And then the negative anion of like Cl negative will be attracted to the positive charge, the positive end of water, so the positive end of water will surround it. And so they'll also mix because the positive and negative are, even though they're attracted to each other, because the water also has a very similar type of attraction, they'll mix randomly. There is a YouTube video which I would highly recommend watching. You can find the link right here. What happens, I think it's a good visual. So if you have like a crystal of salt, so you can see here lithium fluoride, the negative ends of the water molecule will start to surround the positive ion. The positive ends of water will start to surround the negative ions. When the water molecules, when there's enough positive ends surrounding the negative to pull it away from the other positive ions, it will sort of swallow it up, and you can see in the lower right hand corner the water molecules surrounding one of the ions, and it'll pull it away, and then molecules can come in and surround the other ions and slowly pull them away. So that's the dissolution process, or sometimes we also call this the solvation, the dissolving or the solvation process. And again, I would highly recommend watching this video. It shows sort of the dissolution of a salt. Okay, so just like anything, different salts can dissolve at different rates. So it sort of depends on a couple of, the attractions. Again, if some attractions are stronger than others, things won't mix as well. So when we're talking about ionic solutions, we look at, first of all, the energy of hydration, how easily water is attracted to the ions in question. And then we also have the lattice energy, which is the energy holding the solid together. So if the hydration energy is greater than the lattice energy, the solid is very soluble. That means the bonds in the salt are a little bit weaker and they're easily pulled apart from each other. If the hydration energy is less than the lattice energy, then the solid is not very soluble. And so there are ranges for different types of things. Not every single solid, there's different solubilities depending on what we're talking about. So if you think back to your solubility rules, you may or may not remember things like sodium chloride is very soluble, but things like sulfates and phosphates are not very soluble. Well, that has to do with how strong of a lattice energy. So again, the stronger the lattice energy, the less soluble something will be. And the lattice energy then also depends on a couple of factors. The first is the charge of the ion. So the greater the magnitude of the charge, the stronger the lattice energy. So again, thinking back to our solubility rules, if something has a +1 or a -1 charge, they tend to be much weaker than a +-2 or a +-3. So that's why salts like sodium chloride, potassium chloride, lithium, all the +1, -1 ions are much more soluble than those that have, like I said, sulfates or phosphates that have much higher charges. So the charge of the ion is important. And then also the distance between ions is important. Smaller ions can get closer together, so they're more strongly attracted to each other and have a higher lattice energy, and so are therefore less soluble. Now, these are kind of general rules, and there are some complications, and it'll depend on a few things, and it's a little bit beyond this class. But in general, I want you to remember these trends. So NaCl is much more soluble than, say, magnesium oxide, MgO, because NaCl is +1 -1, MgO is +2 -2. But at the same time, something like lithium chloride, LiCl, would be less soluble than sodium chloride, NaCl, because lithium is smaller and can get in tighter than sodium can. And so lithium chloride would be less soluble, sodium chloride would be more soluble, and potassium chloride would be even more soluble. All right, when you've probably experienced this before, if you dissolve something in water, especially an ionic compound, there is generally a temperature change that, excuse me, is either absorbed or evolved. This is called the heat of solution. So if you say you add salt to water, what happens? It generally gets a little bit warmer. We do a lab where back in the first semester where we mix different salts in water and measure the temperature change. NaOH will get very warm. So it's an exothermic heat of solution. Other compounds like ammonium nitrate, if you dissolve that in water, it will become very cold, and that's endothermic. Okay, so what about how temperature and pressure affect the solubility? How can you kind of know this in general. If you're trying to make sweet tea, you try to put sugar in an ice cubes in cold tea, and you try to put sugar, it doesn't dissolve very well. But if you heat the water up and then add the sugar, you can make much more sweet than you were expecting it. So the solubility of solutes is very temperature dependent. However, it will depend on what the solute is. So if the solute is a gas dissolved in a liquid, then actually temperature, if you increase the temperature, the solubility will decrease. And that's the picture over to the left. This is just showing the solubility in water of different gases. And you can see if you look at the green line, O2, as you heat up, the amount of O2 that can be dissolved in water will decrease. So up at 40 degrees, it's like 1 millimolar, whereas at maybe 5 degrees, it's almost 2 millimolar. So the solubility of gases decreases, and that's actually a problem. One of the problems with global warming is that the temperature of our oceans are steadily increasing, maybe slightly, but then the solubility of that oxygen will go down, and so there will be less available for the creatures in the sea. Anyway, now in general, solids are more soluble if you increase the temperature. So most solids will dissolve in liquids at the solubility will increase with temperature increases, and that's the graph on the right. So if you look at, for example, NaCl, the pinkish purple line, solubility increases as temperature increases. They don't have sugar on here, but we know sugar generally increases as temperature increases. You can see there's a few that don't follow that rule. The blue line, cesium sulfate, actually decreases with increasing temperature, and that weird one, the sodium sulfate, will increase to a certain point and then at a certain temperature will decrease. But in general, solubility increases with temperature increases when it's a solid. Now, what about pressure changes? In general, if the solute is a liquid or a solid, pressure changes won't affect the solubility at all. However, if you are trying to dissolve a gas and something else, the pressure change will make a difference. So if you look at the left, where the pressure is low, you can see that there's a lot of gas above the liquid. If you increase the pressure, push it down more, and it sort of makes sense. If you push it down and you increase the pressure, now you see that there are more gas molecules dissolved in the liquid. This is called Henry's law, and it says that the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas in contact with the liquid. So if you increase the pressure of the gas, you'll increase the amount of the gas dissolved in the liquid. And that's exactly what happens with your soda. When it's at the bottling plant, they have very high CO2 pressure above the liquid, so a lot of the CO2 can dissolve in the water to make your carbonated beverage. When you lift the cap, what happens is now the soda is at atmospheric pressure because you've taken the lid off, so the pressure has come down. Well, that gas can no longer stay dissolved in the liquid. It has to escape, and so that's when you see the bubbles come out. Okay. Henry's law expressed mathematically is S equals KHP, where S just means solubility. KH is a constant called Henry's constant, and that will depend on whatever liquid you're talking about. And then P is the pressure. So you can see the main thing to see here is that if you increase the pressure, the solubility will increase because they're directly related. Okay. So I gave you the soda bottle as an example of Henry's law. Another example is when scuba divers get the bends. If you go deeper underwater, your body is under much greater pressure, and so more of the gases that are in your body will dissolve in the bloodstream because they're more soluble under higher pressure. So if the diver comes up too quickly, the gases will come out of solution very quickly. But of course, you've got you've got arteries and things like that, and so those bubbles will block blood flow, and it will cause joint and muscle pain, and that's what's called the bend. So if you're scuba diving, you have to come up very slowly so that you can equilibrate your pressure and allow the the gases to come out of solution slowly. Another example is a hyperbaric chamber. And my aunt actually did this. She had a sore on her leg that wouldn't heal, and so actually if you're in a hyperbaric chamber where they increase the pressure of maybe not total atmospheric pressure, but maybe a higher pressure of just the oxygen, sealed chamber, pressurized, it's pressurized greater than atmospheric pressure, but they could also increase the partial pressure of just the oxygen. So more of the oxygen will be dissolved into the sore, for example, and it will hopefully help healing faster. Or in the case of carbon monoxide poisoning, carbon monoxide and oxygen are very similar in size, and so the carbon monoxide replaces the oxygen receptors. But if you increase the pressure, more of the oxygen will dissolve and hopefully get the carbon monoxide out. I just thought it'd be kind of interesting to just learn a little bit more about the champagne. Actually, anytime wine is made of any kind, during the fermentation of grapes, the yeast will turn glucose to alcohol, and carbon dioxide is a byproduct. But in normal wine production, the gas is released because by valves in the cask. But if you're making champagne, what happens is the winemakers will add more sugar and more yeast to the wine before the bottle's sealed. When the wine ferments a second time, the CO2 then becomes trapped in the bottle. Again, just like the soda bottle, as long as it's capped, the pressure of CO2 is very high, so the CO2 will stay dissolved. Once you open it, the pressure of the CO2 decreases rapidly, which means solubility decreases, and the CO2 has to be released as bubbles.